Recording to the cloud. Okay, so it seems to be working. All right, so these are some trig identities, and we're going to work our way through these as we cover the content in the unit. But these are, when we talk about identities, these are indisputable facts related to trigonometry. It's kind of like along the same lines as when you talk about the commutative property of addition, for example. If I say the commutative property of addition, you might think 2 plus 3 is equal to 3 plus 2. You swap the order and the result is still the same. Right? But that's true no matter what numbers you put in to that operation. So if I say 5 plus 4, that's equal to 4 plus 5. Or if I say A plus B, create a little slider there, A plus B, no matter where I put the A and no matter where I put the B on the slider, will be the same as B plus A. All right, so I'll just slide this up so you can see it side by side, but these are what we call numerical identities. All right, they call them properties, but it's really an identity because it's a fact that A plus B and B plus A are the same no matter what the value is for A, no matter what the value is for B, the result is always going to be the same. All right? So the same holds true for trig relations, right? And trig functions and trig expressions and whatever you can think of related to trig. There's going to be some rule associated with it, or there could be a rule associated with it. Like, for example, I'll actually start off with something simpler than these because I'll get into these in a minute. But something that we know is that tangent is equal to sine divided by cosine, sine of A divided by cosine of A, right? So one way I can verify that would be to go into Desmos under trig. So if you tap on functions, it brings up this submenu here with trig, stats, distributions, and miscellaneous. And in the trig menu, we have a lot of stuff that we would need, one of which is tangent. So I could type in tangent of capital A. I'll add a slider for A. That's going to be equal to sine of A over cosine of A. So back to my function, sine of A divided by function cosine of A. But one of the things that we like about Desmos is that if you can't remember how to get to a function, you just go to the keyboard and start typing it in. If you know the name of the function, Desmos will recognize it. All right. But you can see here that at tangent for this A value of 1, I got 1.557 blah, blah, blah. For sine over cosine, sine of A over cosine of A, I got the same thing. All right. So no matter where I put this value here, that A value, I'm going to get the same result for tangent as I am for sine over cosine. That's demonstrated. It's not a proof or anything, but that's demonstrating the relationship between tangent and sine over cosine. Tangent of A and sine over cosine of A are the same. You see it numerically right there. Right, so that's really, I'll call it an illustration of the identity, but it's really just looking at different examples associated with that identity. Okay, so what we want to do is kind of dive into these identities and see what makes them tick, but then we also want to get to a level of proficiency where we can recall these and reflect back on them in future courses. All right, so you're in Calc 1, Calc 2, it comes up big in Calc 2, right? The trig identities. So, I mean, you'll use them plenty in Calc 1, but you'll really use them, I mean, for like a good chunk of the semester in Calc 2, right? So it's a big deal. But you can also verify that cotangent is equal to cosine over sine, right? But it would amount to the same thing that I did here. So you just change the tangent to a cotangent and change the ratio to sine, instead of sine over cosine, make it cosine over sine, all right? Now, there is a function on the TI calculator. I actually never tried it on this one, so just bear with me for a second. I'm going to try it. I don't expect it to work, but if it does, I'll have an explanation. If not, I'll just kind of pause and explain to you that what I just did is not useful in any way. All right, so let's see. Well, it accepted the command, it just didn't do anything with it. Let me try X. Yeah, okay. Now, because in the TI calculators, you can assess the truth value of an expression by putting it in, or a truth value of an equation by putting it in with an equal sign. And I'll just show you, you know, actions speak louder than words, I guess. So I'll pull up my TI calculator. So what you could do, so on the TI, let's say I wanted to focus on tangent of A is equal to sine A over cosine A. I would actually just type that in. So I'd hit, oh, I hit parentheses accidentally. Tangent. And then alpha A is equal in the math, in this, the second math menu. It brings up test functions. The second math option 1. Sine of A divided by cosine of A. All right. And what it'll do, and again, I don't know how many of you have TI calculators, but if you do, you could try this. It'll bring up either one of two possibilities in the test menu. It'll either bring up a 0 or a 1. If the result is 0, then it's false. If it's 1, then it's true. You could do that for really any kind of equation in the TI calculator. Right? So it's kind of cool. It goes in it because we do most of our stuff with Desmos. This falls squarely in the fun fact of the day territory. But if you're one of those folks that know that you're going to have to at some point transition to using the TI calculator more frequently, then you might take special interest in something like this. You could verify that a relationship is true based off of this idea. You just put it in as an equation using the equal sign that comes from the test menu. And if you get a 0 as a result, it's a false sentence. If you get a 1 as a result, it's a true sentence. Right? All depending on whatever the value of A is. Right? But like I said, that goes under the category of fun fact of the day. If you're not a TI user, then it's irrelevant, but I'm trying to give a little something for everyone. Right? These other identities, the Pythagorean identities, the sine squared, cosine squared, and all that, we'll get to that in a minute. But those are really, really important. All right, you're going to want to memorize these. All right, and I mean that in the truest sense of the word want. You are going to want to memorize these. I'm not going to ask you to memorize them. You've had access to your notes the whole semester, right? When you're taking tests, you'll never need to memorize them for me, but you're going to want to memorize them for future reference, and also just so you don't always have to keep going back and looking it up. This is the kind of thing that you'll just like with the unit circle, you'll find life is so much easier mathematically if you have instant recall. All right, so taking the time to memorize this stuff, it'll go a long way. All right. So, and the functions of the sum of two angles and difference of two angles, all that stuff. We'll get to that in due course. But for now, we're just kind of living in the top little section here. All right. So just the Pythagorean and quotient identities for this evening. So on the next page, a lesson proving trig identities. That's all wonderful. But that doesn't really tell the whole story. We're going to look at the validity of Pythagorean reciprocal and quotient identities. And it's all going to start with this good looking circle right here. And we could actually create that circle on Desmos. And you'll get a copy of this. I'll post it up on Blackboard. If I was able to share my Blackboard screen, I would have showed you the what I've been up to in terms of the calculators that I've been posting. But there's plenty up there, right? But I wanted to show you this one in particular because this is the unit circle, at least in its most basic form. But any circle with a center at the origin can be represented by the equation x squared plus y squared is equal to r squared. All right. So a circle with the center at the origin can be represented by the equation x squared plus y squared equals r squared. And the reason why that's the case is because of what you see there in the form of that triangle. Any point in space can be what we call decomposed into horizontal and vertical components, right? Because any point in space can be thought of as what we call a vector, right? A vector is really, for our purposes, without getting into the science of it, it's a ray, right? It's basically part of a line that starts at the origin, but then increases without bound. But it has some sort of length and some kind of direction. That direction is measured by theta, but the length is determined based off of the radius. Now, if that length goes the same, or that vector goes the same distance in every direction, so the length is the same, then it would trace out the path of a circle, right? So I'll just show you real quick. X squared plus y squared is equal to r squared. Oops, extra jammy there. Slider for r. You see we have a nice circle there centered at the origin. I can make it big, I can make it small. Right? This has restriction of only going out to a radius of 10, but I can make it whatever I want. The unit circle is actually this little guy right here. Right? But we could actually trace out around that circle pretty easily, right? Just by identifying a point along that curve, right? So every point, again, in space is defined as x comma y. So this would have some horizontal distance x and some vertical distance y, right? So what I would do is create some point that I would call x1, y1. Oops. Do that again without the oops. Couple of sliders for it. And you see that this point could be anywhere because I haven't created any kind of restriction for it. All right. So it could be anywhere, but I want it to be on the circle. All right. So what I can do is I can take this equation, x squared plus y squared equals r squared, and solve for y. All right. If I solve it for y, again, I'll just rewrite it. X squared plus y squared is equal to r squared. Knock off the x squared, sorry, from both sides. You have y squared is equal to r squared minus x squared. And then when I take the square root of both sides, I get y is equal to, I'd actually get two equations because when I actively take the square root, I'm looking at a plus or minus situation. right? So what this actually gives me is a function of x, or two separate functions of x. I could write it as f of x is equal to the square root of r squared minus x squared, and another f of x, well, I'll call it g of x to distinguish one from the other, which would be negative the square root of r squared minus x squared. Now, if you just take a look at what happens when I plot this, it's pretty cool. I'll write it as f of x is equal to the square root of r squared minus x squared. All right. It kind of happened so quickly, but we had r squared minus x squared. It actually snapped into the shape of the circle. I'll actually change the color so it stands out. But I had it as r squared minus x under the radical, but the minute I gave that power of 2, it snapped to become part of the circumference of the circle. And in fact, if I turn off my initial equation, you see that I'm only looking at the top half, which is why we need the g of x to be there also. So g of x is equal to, now you can write g of x as the square root of r squared minus x squared. But you could also define it in terms of how it relates to f of x, because this is exactly the opposite. This is my f of x right here. So g of x can be thought of as negative f of x. All right, they're the same thing. All right, so it shows us that if you know the top half of it's a circle, in this case, with a broader topic called conic sections, which is what we're working towards in this unit. If you know something about the top half, then you can draw conclusions about the bottom half. If you know something about the left half, you could draw conclusions about the right half. All right, so that's kind of a cool relationship. But I still want to have this point living along that curve. Now that point I called x1, y1, but I could actually go back now and say, you know what, I want to call it something else. I want a coordinate, but I want this coordinate to only exist on this graph, on the circle, right? So that coordinate I could call x1, comma, f of x1. All right, so what that'll do is it'll give me the y value corresponding with the x value that I have plugged in, or what I will have plugged in based off the slider. And now any point that I decide on will have a corresponding y value that must follow the function f of x, right? And so therefore it has to live on this curve, but it's only going to give me the top half, right? So I just do the same thing, but with the g of x function, right? But you know, that's really not 100% necessary. But let's say I do x2, because you can kind of get an idea of what's going on with just the top half. Is really what I'm getting at. x2 and then g of x2, and create a slider for that, and you have a point that's living on the bottom half. I just kind of hit something funky. So you have some possible points on the top, some points that live on the bottom, right? But really what's happening here is we're seeing that no matter where I slide these sliders, no matter where my x value is, I'm always going to end up with a point that's on the curve, whether it's the top or the bottom, right? No matter how big I make the curve, right, like huge or tiny, the points that I'm working with will always be restricted to that curve itself. All right. So that's telling us that we have a consistent radius. I mean, it's a decent visual. I'll jazz it up a little bit later, but that's really the idea. And so every one of those points has a horizontal distance of x away from the center. I'll just focus on the bottom, the top one, I mean. Every one of these points has a horizontal distance away from the center that we call x, and a vertical distance that we call y. And the relationship is that it's Pythagorean creating a right angle, which is where that x squared plus y squared equals r squared comes from, because that's the Pythagorean theorem, just using these measures as opposed to a squared plus b squared is equal to c squared. All right, so it's actually not so much the case that this circle is giving us the triangle as it is that the triangle is giving us the circle. All right. So then, you start wondering, okay, well, what does this have to do with trig? Well, we learned last time, or 2 times ago, that any point on the unit circle can be thought of as cosine theta comma sine of theta. All right. So any point on the unit circle is cosine theta comma sine theta. So if I have a circle with a radius of 1, so dialing it down to a 1, which, with Desmos, it's fine because even though the circle gets really small, just zoom in. Any one of these points around the circle can be thought of as cosine theta comma sine theta. Oop, wrong one. I'll just write cosine comma sine just for now. I got to put the Greek letter in there later. But that's really what's going on. Any one of these points is cosine comma sine, but only for the unit circle, only for a circle with a radius of 1. All right. So what we want to do is come up with an effective relationship that would apply in all circumstances. All right. So this is saying that the radius is equal to r, but what I would do is I would simplify this by saying, all right, we have a circle. I know I just drew a line, but a circle with a radius of 1. We know its dimensions are x comma y, but really we can think of that as cosine theta comma sine theta. All right. So a couple of things come from this. One is that we have proportional triangles here. All right. So if I take this triangle out and this triangle out and just kind of draw them off on the side if my handwriting will allow that. I'd have a blue triangle here. And I'd have a red triangle, a smaller red one. All right, the blue one, x, y, r. The red one, cosine theta, sine theta, and a 1. All right, so what we would get out of this is a proportional relationship. Right, it's just not necessarily obvious when you look at it when the two triangles are separate like this, but when you look at them side by side, it becomes a little bit more apparent. Right, so then we come up with a few pieces of information, but we can actually kind of clean this up and draw lots of conclusions from this. All right. One is that we would have a proportion where r to 1 is equal to x to cosine. All right. So r over 1 is equal to x over cosine. All right. Another relationship would be that r over 1 is equal to y over sine. For that first relationship, I could actually solve for x and come up with a general rule that x is equal to r times the cosine, just cross multiplying. It's a proportion. Cross multiply. X times 1 is x. R times cosine theta is r times cosine theta. Y times 1 is y. R times sine theta, r sine theta. All right, so we have a nice set of rules here that would allow us to come up with coordinates for x and y on any circle, regardless of the size of the radius. All right, so that's kind of a nifty relationship, because now instead of, you saw all this mess that I did before. It's with the subscripts and everything like that. It's pretty rough to follow. But if I tell you that any coordinate on any circle could be represented by r cosine theta, comma r sine theta. All right, because r cosine theta is the x value. R sine theta is the y value. Right, any coordinate on any circle could be represented by that. All right, so if the radius is equal to 1, then it's just cosine comma sine, because r would be equal to 1. Right, but what I can do here, and let me actually open a new Desmos. I'll save this one, but I'll open a fresh new one. And say, parentheses, r cosine. To get a theta on Desmos, it's the dumbest thing ever. There's no theta key. Oh, it's the dumbest thing ever because the theta key is right there in front of my face and I never noticed it. Right, but okay, so it's not the dumbest thing ever. But if you're ever in doubt and you have trouble finding a Greek letter, just type in the name of the Greek letter and it'll convert it over for you. Theta, Theta, and it'll convert it over to a theta symbol. After all this time, I never noticed it was right there in front of my face. What a world. Universe. So you could just pop it in like that. It'll give you the error because it says too many variables. And that's because we haven't defined anything yet. But if I tell you that r is equal to 1, now we have something going on. And if I tell you that theta is equal to, we'll say, I don't know, 0. Oh, it's not liking my theta is equal to 0, huh? Oh, okay. Let me use a different variable for a sec. Let's use a t for now. Sometimes, sometimes the Desmos has a hard time with the Greek letters. So sometimes we use t for theta. But this creates a function, but you can plot it like that and get a nice circle, radius of 1. That's one option. All sorts of different possibilities. But what we have is a relationship that allows us to come up with coordinates on a circle depending on a given angle. Right? And so that's really the moral of the story here. Use capital A. Make a slider for that. The issue was that sometimes it has stored variables in there, but what we want is the ability to pop in a constant, not necessarily a variable. Right? But this is my r equals 1, same circle, it's the unit circle. And I'm sliding around my unit circle depending on whatever the angle is, A for angle, I guess. And so that shows us the same thing that we saw on the previous page, that r cosine theta will do the same job, r cosine theta comma r sine theta. Right? That's the whole point behind this, is that we can now do what we call a trigonometric substitution that allows us to move away from what we call rectangular coordinates. But that's all based off of this one relationship, x squared plus y squared equals r squared. Right? So if I know that in the unit circle, right? So let me actually just move this up. Well, yeah, I don't really have a choice. In the unit circle, r is equal to 1. All right. Which means that any point can be thought of as x comma y, and that x comma y can be thought of as cosine theta comma sine theta. And that's what I mentioned before. If we know that, and we know that x squared plus y squared is equal to r squared, by substitution, right, so I'm going to bring it in here, we know that the r value is equal to 1, because we're saying it's a unit circle, a single unit. The r value is equal to 1. The x value is equal to cosine of theta. The y value is equal to the sine of theta. So I would say, instead of x, cosine of theta. Instead of y, I would say sine of theta. And instead of r, I would say 1. So if we clean this up, notation-wise, it's kind of weird when it comes to trig functions. This is perfectly acceptable notation, but an alternate form of notation, when you raise a trig function to a power, is to write the power after the trig function itself. So to write cosine squared of theta plus sine squared of theta is equal to 1. It's a pretty common representation. It's just that what they're saying is that it's the cosine function that's squared, not the angle. So the theta representing the angle, that's not the thing that's being squared. It's the function itself. So these two things mean the same thing, but it's very often confused. Also, a lot of forms of technology don't really respond to this. The TIs have a hard time with that, but the Desmos does just fine with it. Right? It just takes a little scrolling and tapping, but you get there. Right? So this is the Pythagorean identity. If we go back, I'll zoom back in a second, but I just want to take you here. Sine squared plus cosine squared is equal to 1. That's the first Pythagorean identity. Right? So just based off of, I mean, it took a lot to get there, but that's what this rule is. Right? It's written as sine squared plus cosine squared, but it's commutative. You switch the order and it's perfectly fine. Right? There's two corollaries to this, right? Two add-ons to this rule. And that is, if I take the cosine squared theta plus sine squared theta equals 1 and divide each part of it by cosine squared theta. We get a new rule, right? So this is one rule. So this is one rule. This is our first Pythagorean identity. All right, and it's called Pythagorean identity because it's based off the Pythagorean theorem. Right. The second one, if I divide each term by cosine squared divided by cosine squared, I mean, you don't have to be a master of trig in order to know that anything divided by itself is going to be equal to 1. Now, a rule is that tangent of theta is equal to sine of theta over cosine of theta. All right, we talked about that last time, or last lecture. So I can apply that here. I mean, they're squared. All that's going to do is give us a tangent squared. All right, and then 1 over cosine. Actually, I can just kind of shove this down a little bit. So this is another rule. I'll say rules.
Wait, but isn't tangent squared theta 0?
Tangent squared theta? No, tangent squared theta would be a function. It's only 0 when theta is equal to 0. All right, so one of the rules is that tangent is equal to sine over cosine. Another rule is that secant of theta is equal to 1 over cosine. All right, and so 1 over cosine squared would be secant squared for quality theta on the end here. All right, so that's our second Pythagorean identity. Oh, it won't lock because I skipped over a value there. All right, so that's our second Pythagorean identity. Our third one comes from taking our original or our first Pythagorean identity, cosine squared theta plus sine squared theta equals 1, and dividing each part of this by sine squared theta. All right, so more rules. It's trig, so it's all rules all the time now. It's just a question of trying to understand the rules and why they work the way they do, because the more you do that, the easier it is to kind of move on to the next level. If you get to a point where you're not constantly memorizing everything that came before, then you'll be better off for it. But until we're there, it's just rule after rule. So here's another one. And again, we talked about these last class, but that doesn't mean, or last lecture, that doesn't mean that you memorized everything instantaneously. So cotangent of theta is equal to cosine of theta over sine theta. And then the other one that's going to be relevant here is that cosecant of theta is equal to 1 divided by sine of theta. All right, so cosine squared over sine squared would be cotangent squared theta. Anything divided by itself is 1. 1 over sine squared. Well, 1 over sine is cosecant, so 1 over sine squared would be cosecant squared. So that is our third Pythagorean identity. All right. So we have 3, but really it's just the one that's been modified into two other forms. All right, different like phases of water, I guess. Like there's water, then you boil it, it becomes steam, then it condenses, and then you got your solid state. It's really these are just the different phases of the Pythagorean identity. Right, the first one is the most important one because that's the equilibrium state. But then from there, you make some modifications and you get a new form, but they all amount to the same thing. All right. The first two are the most important ones. First one being the most important, the second one being the second most important. But what I can say is that they'll come up very frequently. All right. In your studies involving trigonometry, the last one I hardly ever see. All right. So if you're going to ignore one, it would be that last one. But those are the Pythagorean identities, and this is kind of the origin story, and it's a lot of origin, right? But it all has to do with one circle. It all started with a mouse. It started with a circle centered at 0, 0, and we were able to get all this information from that circle, right? So just so much going on there, but it's all meaningful, right? Now, what we need to do is use some of these identities to help us prove or disprove. And for our purposes, we're only going to worry about proving other identities, right? So you can see the blurb there. There's helpful hints, but it's the kind of thing where until you sort of dive into an example, you could see the helpful hints. It's like I don't even know what these are helpful hints for. So it's, if you get stuck on one side, try the other. It's like, what are you even talking about? So we'll tackle an example or two or three and then go from there. All right. Some of them are really easy. Some of them are a little bit more challenging. Most of them will involve algebra in some capacity, but they'll all involve a trig identity in some way, shape, or form. So I chunked this up so that we wouldn't, you see all these identities. We're not going to do all of them on the first page. The first page will tackle the first little chunk of identities. The second page will tackle the next couple of chunks, and then you get the idea, all right? So it's chunked. Or the first couple of pages, the first chunk of identities. So looking at number one, the whole idea when it comes to proving identities is to modify the equation so that the left side is equal to the right side without multiplying, dividing, rooting, or anything like that to both sides of the equation. So we don't want to use any properties of equality, right? So we're not using properties of equality, which just means that you can't add to both sides. Like I can't like divide both sides by a cotangent x or anything like that. What I have to do is I have to work each side of the equation independently. So what I do, and I've done this for years, and I've recommended the same approach, and it seems to work. What I do is I draw what I call an impenetrable barrier, otherwise known as a vertical line, down through the equal sign and straight on down through as much of the workspace as I want. A little reminder to myself that I'm going to do stuff to the left side of this barrier. I'm going to do stuff to the right side, but I'm never going to do stuff simultaneously, as in I'm not going to divide both sides by 10 or raise both sides to the second power, nothing like that. Whatever happens here stays here. Whatever happens here stays here, right? So I look at this basically as if it's its own problem and ignore the other side completely. So I'd look at this and I'd say, okay, what do I have? I have a sine function multiplied by cotangent. So I'd say, what do I know about sine function? I know it's got a graph and it's got, you know, a shape like this. It looks wonderful. All right. Cotangent, I know that that's equivalent to cosine, in this case, the variable is x, cosine of x over the sine of x. All right. I know that because we just did that, number one, but also right here, right? It's one of our identities, right? Identity being the word of the day. Identity, like the born identity. All right. So I'm going to take that and multiply it by the sine of x that's already there. Now, multiplying two fractions requires you to multiply the numerators together and the denominators together. All right. Well, this first fraction, quote unquote fraction, doesn't have a denominator, so I'll give it one. So this would be the same as saying sine x times cosine x over sine x. Well, I have a common sine x top and bottom. They would cancel away. Basic algebra, nothing too fancy there. Once I do that, I see that the only thing that remains is the cosine of x. That happens to be the other side of the equation. So my impenetrable barrier didn't need to be so long, because after a couple of steps, I was able to demonstrate that just through a couple of modifications, just a couple of substitution, well, one substitution and a little bit of algebra, I was able to get the left-hand side to be equal to the right-hand side. And so that's a proof. I just proved that this is an identity. It's a true relationship in all cases. So that's really it. I mean, it can be that easy. But it is reliant on you being able to recall this rule. Too thick. Cotangent being equal to cosine of x over sine of x. You see it's cotangent of x here rather than theta, rather than a. You know, we can change the argument and that's perfectly fine. All right. So let's do another one. Number two, and you'll see in a lot of cases, it comes down to your ability to diagnose, you know, what's going on within the identity, because you'll look at it and say, well, in number two, I have all cosines and sines. I don't know what to do here. And then you look at your rule list and you see, and well, I don't see a rule related to what I have written here. However, I'm going to draw my impenetrable barrier. Boom. Okay. Boom. I have this expression being raised to the second power. So I'm going to write that as cosine x minus sine x times another cosine x minus sine x. I mean, that's what it means to square something, right? Multiply it by itself. This is a binomial squared, but it really is just a matter of distributive property. So I'm going to take this cosine, multiply it by that cosine. Cosine squared x. Because cosine times cosine is the same as cosine x quantity squared, but this is the notation that represents a cosine function being squared. Then I'm going to take that cosine, that first cosine, and multiply it by a negative sine. Now, the best I can do here is just smush them together. cosine times negative sine would be negative cosine x sine x, or sine x cosine x, it doesn't matter. Right? Then what I would do is take this negative sign and multiply it by the cosine. So negative sine x cosine x. All right. And then I would take that negative sign and multiply it by another negative sign, which would give me a positive sine squared x. All right. I have some like terms. It doesn't seem like that initially, but they are, because these have the same ingredients. It's just one has the cosine first, then the sine. But I could easily rewrite this. Cosine squared x. Then I'd have minus cosine x. Well, actually, I'll go with the sine x first. Because the other one I could just lift as is. A little bit of convenience here. Just drag it on down. Now, again, commutative properties at work, but before we do that, we have these like terms that could be put together. Despite how disgusting this looks, and that's not really the point. I guess that's all right. It really has more to do with the fact that no matter how complicated an expression looks, the rules of algebra still are at work here. Like, for example, if I don't have a number in front of an expression, it's assumed to be a coefficient of 1. Same deal here. These are two like terms. When you put them together, -1, whatever follows, minus 1, same thing, same expression, is going to give you a -2. But in this case, instead of it being something like -1x minus 1x, it's -1x, -1 sine x cosine x minus 1 sine x cosine x, which is going to give you -2 sine x cosine x. So much more elaborate, but it's still all there. And so I'll bring everything down along for the ride. Now, this is what I meant with the commutative property. I can take this and move some things around. Because if I can group the red stuff together, that's actually an identity. That's the Pythagorean identity. That's what we just spent a whole page trying to learn about. Cosine squared plus sine squared. We're just missing the other half of that identity. So the rule here is kind of going back. Cosine squared, well, regardless of what the variable is, cosine squared plus sine squared is equal to 1. So this whole expression here is going to amount to just a 1. And everything else comes along for the ride. Now, the one thing that I do caution you to do, or recommend that you do, is every now and then have a look at the other side of the equation, because I know I create this impenetrable barrier. Yeah, I don't want to cross this barrier. I don't want to bring anything over from one side to the other. However, you do have to give it a look every once and again in order to get a sense of whether or not you're done. Like, for example, if I never looked at the other side of the equation, I wouldn't realize that I just finished the problem, right? Because I got equality. The left side and the right side are equal to one another. Because I've had many instances where students would come to me and say, I'm really struggling with this trig identity stuff. And I'll be like, which question? And it'll be like number 2. They'll say, I got up to this point here. I don't know what to do now. Be like, did you look at the other side of the equation? Because you got up to that point and you can't figure out what to do anymore because there's nothing else to do. Right? So you were already done with the problem because you got the left side to be equal to the right side. So be on the lookout for that kind of thing. And in order to be on the lookout, you got to every now and then at least glance to the other side of the equation. Now, we've only been working on the left side of the equation because the left side has been the side that's more complicated than the right side. Like, for example, if we look at number 4, left side is pretty nasty. Right side is nice and simple. Like, if we're going to be able to work one side of the equation, it's probably not going to be the right side. There isn't much to do there. But on the left side, I have some algebra that I can work on. Right? So a little distributive property, first outer, inner, last. All right, so I would take this 1 and multiply it by this 1. Then I would take this 1 and multiply it by this cosine. So plus cosine x. Then I would take this cosine, negative cosine that is, and multiply it by this 1. So minus cosine of x. And then I would take negative cosine and multiply it by positive cosine. Which would give us a negative cosine squared x. All right. See, we have opposites here. Cosine and negative cosine will cancel away because they're exact opposites of one another. So I could then say 1 minus cosine squared x over cosine squared x. Now there's 2 ways that you can go from here. And that's the thing about a proof. Sometimes your brain will take you in one direction. It'll be different from the direction my brain takes me in, but we're both right. All right. So just going back to that Pythagorean identity, I'll just make a note here, just like right on the top. The rule we know is that cosine squared x plus sine squared x is equal to 1. All right. Or thetas, cosine squared theta, or cosine squared a, or t, whatever. Now, if I were to subtract, in my rule, subtract the cosine squared x from both sides, I get another rule, and that is that sine squared x is equal to 1 minus cosine squared x. So out of a necessity, we just invented a new rule. Because I needed to do something with this 1 minus cosine squared x, I went back to what I knew and I realized, oh, wait a minute, I can look at it in a different way. And that different way gets me to a sine squared. So that tells me that this expression can now be written as sine squared x over cosine squared x. Well, sine over cosine is tangent. So sine squared x over cosine squared x would be tangent squared x. And that happens to be the same as the right-hand side. All right, so it takes a little doing, but it's definitely manageable. But it's very easy to get stuck on a problem. Right? There's an element of perseverance that comes into play. Right? But being able to apply these rules to be able to simplify expressions is really important. Right? You don't necessarily realize just how important it is until you get to a moment where it's like, oh, unless I'm able to simplify this, I won't be able to continue with the problem. That's where we get jammed up. Right. The remaining problems on this page, You know, they can be a little funky, but they're doable. So I'm going to put stars on them. What I wanted to do, kind of something a little different. On Blackboard, I'm not going to put stars on these problems because I want to go over these, especially with that scary one that has power of 4. It's actually one of the easier problems on these pages, but it's intimidating to look at, and that's enough to get people to not want to do it. And this one involves a little bit more algebra, so I'll save that for next time also. But I wanted to do number 9 with you because I wanted to do an example that involved multiple variables, right? And show you just how scary something can look, but actually not be too bad. So I also put on Blackboard. I don't know if it's going to work now. It's probably going to still glitch on me. Yeah, it's still, my whole internet is frozen. Let me just check something real quick. See if I can at least X out a tab or 7. Yeah. All right, well, in Blackboard, there is under Unit 3, right at the very bottom, there's an assignment. I'm not going to actually ask you to solve anything. I just want you to, when we do the solution together, I want you to take a picture of your work and submit it. I'm calling this I'm pulling it up on a different computer. I think I'm calling it a check for attentiveness. So it's a little 5-point quiz, just as anybody who's here active and engaged and focused is going to get a free 5 out of 5 quiz grade. All right, so that's good news. All right, so again, and you know, unfortunately, I'll have to fight the battle with the folks who will say, I didn't know. I'm like, well, you didn't know because you weren't in class. But anyway.
When's this due?
I'm explaining it now. So,
okay.
So what you're going to do is you go to course content. You click on Unit 3. Right at the bottom, it says quiz, check for attentiveness. All right. And all you'll see here, well, you'll see when it, you know, the due date, Wednesday, November 10th at 8:15 p.m. All right, by 8:15 p.m. All you'll see is please handwrite the notes indicated in class by the stated time to receive credit. This will count as a 5-point quiz grade. Late work will not be accepted. All right, so all I'm asking you to do, just to be very clear, I'm not asking you to figure anything out. All I'm asking you to do is just jot down these notes that I'm about to do for you with number 9. So, you know, on a separate piece of paper, write number 9. I mean, if like, what do we got here? Page 50. Okay, I'll even format it the right way. All right, you'll write your name. You'll put number 9. And then what I'm about to write, all I want you to do is take a picture of that and submit it on Blackboard. All right. It's a free 5 points for you just demonstrating that you're part of the action tonight.
Professor?
Yeah, what's up?
I usually do my notes on like the notepad. So would a file submission be fine?
Well, it's got to be handwritten, but as long as
Okay.
it's your handwriting, that's fine.
Okay.
Yeah.
Thank you.
Yeah, the reason I want handwriting is because I tried to think of all the different possible ways that people can game the system. I can already see somebody being like, oh, you just want the solution, and then they put it into some photo math or something like that and submit that. I was like, no, just give me something handwritten, for crying out loud. It could be digital inking, that's fine, but whatever makes sense as long as it's your own hand. All right. So anyway, very simple problem. Nothing too crazy, but it is scary looking. All right, and this is why, one of the reasons why I want to make sure everybody gets this down, because this is the kind of question I'll put it on a test, and you'll be terrified when you see it, but it really won't be that bad. Now, that being said, pretty sure there's a typo in it, but why wouldn't there? Yeah, these are backwards. This is the problem when I make up a question off the top of my head, but it is fixed now. I'm just doing it in my head real quick, making sure. Yeah, okay. So we'll find out in a second. Anyway, that's not really the point. So impenetrable barrier. Right? Impenetrable barrier. The more complicated side is the left side. But that doesn't mean that there isn't something we can't do. I mean, we might be able to do something on the right-hand side, but it doesn't look that way. On the left side, I see in the numerator really just more algebra than anything else. Now, there's a common 2, so I can pull that out. Cosine Q minus cosine squared Q minus sine squared R. All right. Now, this is not a rule. All right. This expression here is not a rule for a bunch of different reasons. All right. The first thing that I want you to consider is that the arguments are different. And what I mean by argument, again, is the term that's contained within the trig function. One's got a Q, the other's got an R. I tried to choose letters that I knew would stand out, you know, like Q and R. I mean, what's more different than that, you know? So they're not the same. So even if this were a plus sign, let's say this were a plus sign, I would not be able to say that this is a 1, right? By the Pythagorean identity. That's not a thing, all right? Because those letters are different, right? But this looks like a difference of perfect squares, right? This is factorable, right? And really the lesson that I'm trying to get across here is that you don't always have to go looking for a trig rule. Sometimes it's an algebra rule, a basic algebra rule, yeah, but still an algebra rule. Now, the thing is, a basic algebra rule could look really hideous when you throw some trigonometric expressions in, right? So let's not forget that something as simple as, and I'll just do it off on the side, a squared minus b squared is the same as a plus ba minus b. All right, that's an algebra rule. All right, that's just a rule of factoring. So now I kind of look at that and I compare it to what I have here. All right, well, instead of a squared and b squared, I have cosine squared and sine squared. All right, ultimately, that's going to amount to the same thing, because if a is equal to cosine of q and b is equal to the sine of r, then I would get this expression here. I'd have cosine squared q minus sine squared r, the expansion of which would be cosine q plus sine r times cosine q minus sine r.
Do you want us writing this down as well?
Yeah, it's part of the solution.
Okay.
All right. So that would be the nice expansion of cosine squared q minus sine squared r, but that's actually the key to everything else. It's the key to getting us through the rest of the problem, because now I can replace the numerator, or at least part of the numerator, with this expression, or the product of these two factors. Line here. So the bottom of the fraction, copy, the bottom of the fraction is sine r plus cosine q, right? Which is exactly the same, just in a different order, but by commutative property, it's exactly the same as cosine q plus sine r, right? So my next line here would actually just have us swapping the values in the denominator. And, you know, as aggravating as this could be, because it's a proof, you really can't skip this step, right? There needs to be a logical progression from one step to the next. Right? So now I have a nice common factor here. Cancels away. So now I have 2 paren cosine q minus sine r, which if I distribute, run the 2 through, distribute the 2 to each term, 2 cosine q minus 2 sine r, and that happens to be what the right-hand side of the equation is. All right. So this algebra rule, I'm just going to reduce it in size and just kind of tuck it in here. Maybe a little, kind of jazz it up a little bit. And throw a little asterisk on it. But that algebra rule ended up being the key to the whole thing. And again, just some basic algebra rule. Or really, when you think about it, taking a look at what we did here, you could, I mean, I could have started the whole unit with this. Like, forget about unit circle and all that stuff. If I gave you this, I mean, we could have actually done this problem 2 classes ago, because there's really no trig in here, right? We didn't apply any trig properties or rules or identities. All it was just applying an algebraic concept. But in doing so, we were able to take something that looked disgusting, the 2 cosine squared q minus 2 sine squared r over sine r plus cosine q, and it's really just simplifying it down to just 2 cosine q minus 2 sine r. Right? In the next couple of classes, I'm going to show you why we're doing this, because what we need to really get to a point to do is be able to solve equations using techniques like this. But if we're going to solve equations, I don't need to be a mind reader to say, I think you'd rather work with an expression that looks like this than an expression that looks like that. Right? One definitely looks a whole lot more manageable than the other. All right. So being able to transition from the complicated to the simplified is really, really important. Right. So that's where we're going to leave it for this evening. All right. So I'm going to try to get the attendance squared away. I'll do it on my other computer, but I saw in the chat that a few people came in, so I'm going to take care of that. But if you're not sure, or if you haven't checked in with me and you came in late, make sure you do so before you go. Otherwise, have a wonderful evening, and I'll see you all. Today's Wednesday, right? So I'll see you all on Monday. Yeah, Monday. All right, so let me stop.